First, we'll define electric potential. Let me write the definition. At a point is defined as work done per unit charge in moving it work done by an extra agent. Work done. Anyway, I can adjust things. Oh, I'll move it. Work done by an external agent per unit charge in moving it from infinity to that point. Okay, this is defined as the electric potential. The symbol what we use is capital V. From that point, okay, and what are the conditions? The external agent should move the unit charge slowly without acceleration. Okay, there's a condition. It should move it very slowly. Suppose I have here a point charge. Or this one. So I'm an action agent. So here is what the charge plus Q charge, which I'll be holding it. This is the point charge. It is a fixed here. This will not move. This is what initially the separation is infinity. And finally, I'll bring it to a point which is at a distance r. So what this action agent will do, he is a person. What is action agent? Some agent who can be that one. So to make you understand, I'm bringing the idea of person. So what this action agent, he will hold the unit charge and he'll move slowly from rest to rest, from infinity to that point. How much of work done by him per unit charge to move the charge slowly from infinity to that point is defined as the electric potential. Okay, now when it's moving slowly, what actually happens? We'll see somewhere here. There's a unit charge, it will be positive. So how the electrostatic repulsive force will be acting in this direction. The work done by action agent should be in this direction. And what this action agent, you have to shift this charge slowly from infinity to this particular point. So you should do work against this electrostatic force, no? It should do work, or you have to move it slowly. So now work done by action agent. So what is the definition? Work done by action agent per unit charge. Now what is work done by action agent? Will be, should be equal to Fxnl dot dr bar by Q. In moving charge from infinity to that particular point. Now you look at the, as it is moved slowly, so Fxnl should be equal to Fe. What is Fe? Q by R. Then how do this external force and how we measure R? R I'll measure from here, no? So dr bar will be negative. So therefore, because as the person move the test charge, what will happen to this value of R will decrease here. So dr bar will be decreasing that one. So therefore negative sign is brought. So dr infinity to R by Q. So this will become KQ R. Sorry, R square it is. R square dr by Q KQ okay, further this will become is equal to minus K. Integral of R to power of -1 will be -1 by R, infinity to R. So finally, I'll end up with the equation potential at point P is equal to KQ by small r. This will be our answer. Now, what is the unit for this? The unit for this will be volt or joule per coulomb. The SI unit is what? The volt, what we take it. Huh? This is the unit. Like this, the potential idea is brought here. So now how that, so for positive point charge, what is the potential? Will be positive, means like if there's a point charge. Let me describe few things. So at a distance R1, what is the potential? Will be at point 1. Next, let me define at various points. So then at a distance R2, what are the potentials at 1 and 2? Potentials at 1 given by KQ_R1. Potential at 2 is given by KQ by R2. Potential similarly due to negative charge. Potential at 1, it will be minus KQ by R1. Potential at 2 will be minus KQ by R2. Potential will be positive or negative. It all depends upon the type of charge. Then similarly, if there are more than 2 point charges are there, suppose this is R, this is R. What is the potential at point 1? There is a charge. Potential at point P is given by KQ1 by R, KQ2 by R. Similarly, potential at point P is given by KQ1R minus KQ2 by R. What you should do, potential is a scalar quantity. Electric potential, let me write it here. Electric potential is a scalar quantity. So therefore, so what is the resultant potential at a point? Should be the algebraic sum of potential due to individual charges. At a given point potential, okay, let's analyze further. If there are 2 identical point charges are there. Let me discuss all the possible cases. Okay, now here both are positive, one positive, one negative. This case no data. Okay, the 3 situations is what I have. Okay, let me analyze the potential at these 3 cases one by one. So first, potential at point P. I'll add up due to each point charge, KQ by R, KQ by R. See, at point P due to this charge, KQ by R, due to this charge, KQ by R. So total how much it will be? 2 KQ by R. What is the field strength at point P? So there's a 1, there's a 2. Due to 1, the field strength will be E1 like this, due to this E2. And we know E1 equal to E2 is equal to KQ by R square. And what is the resultant field at point P? E1 bar minus C2 bar. So this should be equal to 0. So at point P in the first case, what is the field strength? What is the potential? Non-zero. But what about the field strength? Will be zero. Can happen. Huh? Do remember, very important. The field strength here will be zero, but potential will be non-zero. That is one of the case. Just I'm trying to give a better picture about the potential and the field. We are trying to compare both at a given point. Next situation. Let me call this as 1. This is 2. Potential at point P is given by KQ by R minus KQ. Why this? Because the negative charge. No? In fact, it is like this. The resultant will be 0. What about field strength? Due to positive charge, E1 will be towards right. Due to negative charge, also towards right. The resultant field will be E1 bar plus E2 bar. Both will be directed in same direction. So what is the resultant field? 2KQ by R square. Will be directed towards right. Look at here, potential is 0. Electric field strength is non-zero. Possible, no? So no, nothing. So it can. Similarly, third situation, the potential at point P will be non-zero. The potential at point P will be non-zero. Potential at point P will be K 2Q by R plus K minus Q by R. KQ by R. Field strength at point P. E1, E2. I'll add up 2KQ by R square plus KQ by R square. 3KQ by R square. So there's a field towards right. Both are non-zero. Fine. So all possibilities are there. Then at infinity, what will happen? At infinity, in all the cases at infinity, potential and field both will be 0. At infinity, in all the cases at infinity. So in this way, what we can conclude here, for a point charges or for point charges, we can bring a situation of this kind. So when you're calculating potential, what you should do, take the algebraic sum of potential due to individual charges. When you're calculating the electric field, you should take the vector sum of electric field due to individual charges. I think there's a conclusion which I should conclude here. The resultant potential, there's an important conclusion. The resultant potential at a point is equal to algebraic sum of potential due to individual charges. The resultant electric field strength at a point is equal to vector sum of field due to individual charges. So this is about the vector sum, the very specific these words, vector sum, algebraic sum, hope you are able to correlate things, electric field, vector sum, potential, algebraic sum, because potential is a scalar quantity, electric field is a vector quantity. Like this, for more than one point charge also, we can find out the resultant potential at a given point. Okay, what all we are discussing is again confined to only the point charges only. Okay, let's see that what is the, sir, what is use of this potential?